This is FE Peer Review, the Flat Earth Peer Review channel. The date is June 23rd, 2020. The Great Umbra Penumbra Debate. This is not a response to a specific video, rather it is a discussion of a phenomenon that is much in the air at the moment, the Great Umbra Penumbra Debate. Now really, it's not much of a debate. We all look at the shadows and see it. The question is, what conclusions do we draw from what we see? When I was at university a long time ago, studying for my master's degrees in architecture and structural engineering, one of my courses was in designing buildings to take advantage of natural daylight. During this course, we did a project where we measured the umbra and penumbra of a 10-story building on our campus and derived from these measurements that the sun had an angular size of 0.5 degrees. Before we get completely into it, I want to touch on a few background points. In this image, the blue circle represents an object casting a shadow. It could be Earth, it could be a light pole. For our purposes, it doesn't matter. The red circle represents a point source of light. I've had to draw it with some dimension so that you can see it, but let's imagine it's a tiny point casting light. If close to the pole, the shadow it casts will be widely splayed. But if it is further from the pole, the splaying in the shadow will be reduced. Here we see light from the medium distance point, and we can compare the two splayed shadows. The unshaded lines represent the shadow from the close source. The gray area represents the shadow from the medium source. Now, if we move further away still, our point source casts an even narrower shadow. There are two conclusions to draw from this. The shadow still splays outward. The farther we go, the closer the edges get. But we have to go all the way to infinity for them to be parallel. We can't go any further than that. So a point source can never make this shadow get narrower farther from its object. That is, it can't make the shadow get narrower than the object that's casting the shadow. Now let's clean up this image and look at our distant point source. We have a shadow that is narrowly splayed, and though we can't ever get the splay to become parallel, eventually our point source would be so far away and our shadow edges so close to parallel that we would find it very difficult to measure any splay at all. But now we get into the penumbra, because we are no longer talking about a point source. We have a sun in the sky with a measurable angular size of 0.5 degrees. How does that affect the shadow? For a start, we need to understand that every point on the surface of the sun, just as on a light bulb, is casting light in many directions. So if we look at a point on the sun at the bottom of the circle, we see that it is casting light in the direction of the Earth in such a way that the Earth's shadow is asymmetrical from the line connecting the centers of the sun and the Earth. That would be this narrow dashed line. Likewise, if we look at a point on the sun at the top of the circle, it's casting a similar shadow in the opposite orientation. Now, of course, every point on the sun that has a line of sight to Earth is casting its light towards the Earth. I've simplified these diagrams just to show the extreme edges. So when we look at the light from the sun casting what are effectively lots of shadows that overlap, we see a zone of shadow that is entirely in the dark. And on either side, we see zones where shadows cast by one part of the sun are lit by the other part. Consequently, they are not fully in the dark. I've simplified it in my diagram by only showing the extremes, but when you consider all the points on the sun, then the zone I've shown as light gray, here and here, becomes a gradation from fully shaded to fully lit. Fully shaded to fully lit. I wanted to show here how a similar effect could be achieved by 2 point sources. In this case, we would get the shadow as I've shown it, with 3 distinct zones and umbra and penumbras on each side. The penumbras would not be gradients. You sometimes see this effect when you walk down a city street at night, and closely spaced streetlights cause multiple overlapping shadows. But returning to our main subject, we've seen what a sun with measurable angular size does to shadows. But that leaves us with the question, does it matter how large and far away the sun is if the angular size is the same? Here we see a point on the blue circle representing someone looking up at the sky and seeing a sun of an angular size of 0.5 degrees. That sun could be small and close, or it could be large and far away. In both cases, it would appear the same size to the person looking up at it from Earth. So looking at these 2 possibilities, what happens with shadows? On the lower image, we see a small sun. I've kept the larger off to the left just for reference. The small sun casts overlapping shadows and gives an umbra and penumbra. Looking at the larger sun in the upper image, we see that it does too. But in fact, there is a visible difference between the 2. In the lower image, with the close and small sun, we see that the Earth's full shadow, the umbra, actually gets wider the further it gets from the Earth. Note the dashed lines, dashed white lines, which are parallel at the Earth's diameter. In the upper image, on the other hand, we see that the umbra actually does get narrower with distance. Note again the white lines. The reason for this is because the sun has a larger diameter than the Earth, while in the lower case the sun has a smaller diameter than the Earth. From this we can conclude that it is actually possible, through a very close measuring of objects' shadows, to determine a distance to the sun. Now in reality, it would be a very imprecise result because of the practical problems of identifying the edges of the penumbra. Nonetheless, we could definitely determine one very important fact. If we meet the case in the upper image, the umbra actually does shrink. If we meet the case in the upper image and the umbra actually does shrink with distance, then the diameter of the sun must be larger than the diameter of the Earth. I'm not going to do a full geometric proof of that here, but a careful analysis of this image should make that readily apparent to anyone with knowledge of basic geometry. If any of you are interested to pursue that point, I suggest starting by looking at a sun with a diameter equal to Earth and of the angular size we see. Compare that to the previous cases. A similar but not identical type of geometric analysis could be done with the observation made by Mr. Sensible and discussed by Mr. Thrive and Survive in the videos linked in the description. We would need to know the diameter of Mr. Sensible's small circular card and the distance between his whiteboard and the furthest point from which he cast that shadow. We would also need measurements of the umbra and penumbra from that furthest point. I may conduct such an observation later this summer. Meanwhile, if anyone else is thinking about doing something like this, I'd appreciate hearing about it. As always, likes and subscribes are welcome. I hope you found this information interesting and useful.